jump right into the rules. This is shared with you so you can follow along that way, or just take notes however you prefer. But the first rule that we are going to learn is called the product rule. And the product rule is going to be used whenever you're multiplying two functions together. And so I'm going to write this as d dx of f times g, where like f and g are separate functions. So we have one function times another one. So this would not be a constant multiple rule. And the way we take the derivative using the product rule, you can't just take the derivative of each factor. You take the derivative of one piece of it times the original of the other. So I have like f times g prime plus, and then you take the derivative of the other one times the original of like the second factor. So basically you are taking the derivative of each part, but you have to multiply that by the original kind of other factor. So what this looks like if I'm taking the derivative of x to the 7th sine of x, so I'm going to call x to the 7th f and sine of xg. I want to find f g prime plus f prime g. Technically the order wouldn't matter since we're just multiplying and adding, but what this ends up looking like is x to the 7th, the derivative of sine is cosine, plus the derivative of f is 7x to the 6th, and then the original g is the sine of x. Now this rule also does come from like the traditional definition of the derivative. It's a little bit more complicated to prove, but that is the first rule that we have. Any questions on the power rule? All right, so we have the power rule, and then we also have, I call it, I don't actually know if it has an official name, but I call it the extended product rule. And so basically when we have the product rule, that's for when you're multiplying two things together. Well, we know sometimes you can multiply 3 things together, 4 things together, 5 things together, and so we have this extended product rule. I'm going to go ahead and give it to you directly, but then kind of show you where it comes from. Whenever you have more than 2 factors, you basically just kind of take turns taking the derivative of a factor. So maybe the first time you do it, you take the derivative of the last factor, plus then you take the derivative of the second factor, plus then you go back and take the derivative of the first factor. So you kind of rotate through. If there's 4 things being multiplied, then you just kind of cycle through it that way. The other way to do it is you can think of just the regular product rule and kind of think of like the product rule inside of the product rule. So I might group 2 things together and think of this as like f times g times the h. So if I just use the old-fashioned product rule, I would have like the first times the derivative of the second plus now taking the derivative of the first times the second, distributing that h across. We do see this is where the extended product rule kind of comes from. And that way works. It's a little bit longer, but it is definitely an acceptable way. So if I'm taking the derivative of the example I have here, we know it's the product rule because I have 3 things being multiplied together with an x in them. So I just take the derivative of one piece out of a time and then kind of add my answers together. So I have x squared, x plus 2, the derivative of sine is cosine, plus x squared, the derivative of x plus 2 would just be 1 times the sine of x, and then plus the derivative of the first piece times x plus 2 times the sine of x. Any questions on that? Does anyone see a way you could have done that example and avoided using the extended product rule? Another way to do it then, again, anytime you rewrite a problem, as long as you use proper algebra, you're going to get an equivalent answer. So another way you could have done that example is actually before you found the derivative, I'll move up my screen, is you could have just rewritten the problem using algebra. So I could have rewritten this problem as y is equal to distributing the x squared across. So that's going to become x cubed plus 2x squared times sine of x. And then I can take the derivative. So I have the first times the derivative of the second, and then plus the second times the derivative of the first. This answer we have right here is equivalent to the one that I found in red. And that's kind of true for any of these problems we do with the derivatives. If you want to simplify it before you take the derivative, and as long as you simplify it correctly, then you are going to get an equivalent answer. Sometimes you will have a simplified answer as well. So that's the product rule. We also have the quotient rule. And the quotient rule is used whenever you're dividing two functions. So you have like an x in the numerator and an x in the denominator. And when I'm taking the derivative of that, the formula you're going to use, I'm just going to go ahead and write it out. So I have f is the numerator and g is the denominator. And it will look like this. So it looks similar to the product rule in some ways. You have like some of the original and then some that are the derivative. But you basically have the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the original denominator squared. The order you subtract didn't matter, so it does have to be like g f prime multiplied together minus f and g prime multiplied together. And that's the quotient rule. Again, there is no formula sheet on the AP exam, so I think this is a little bit trickier one to memorize. So lucky for you and probably not so lucky for me, when I was in AP Calculus back in the 2005-2006 school year, my calculus teacher taught me a song to remember the quotient rule. And to this day, that is how I do the quotient rule. So I've never, well, I did it earlier today, but yes, you're about to get to hear me sing a song about the quotient rule. So I'll be singing in a room by myself and you will just get to enjoy it. And if you judge me, I don't care because I probably judge you. So this is the song that I used to memorize the quotient rule. It is to the tune of Old MacDonald Had a Farm. And how I use this song is just to make sure I do the order correctly. And I mean, who doesn't love a song in math to memorize stuff? So when I say low, I'm talking about like the denominator. When I say high, I'm talking about the numerator. And when I say like the letter D, I'm talking about like the derivative of. So like when I say D high, that's like the derivative of the high part of the fraction, the derivative of the numerator. And so the song is, I'm going to say it first, and then I'll give you one chance to hear me sing it. But it's low, D high. So we have low, D high, less, high, D low. Draw the line, and down below, the bottom squared will go. And that's how we do the quotient rule. So for the singing part, it goes low, D high, less, high, D low, da 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 da. Then draw the line, and down below, the bottom squared will go. And there you go. Now you can probably laugh at me in silence. But that is how I remember the quotient rule. Now, whether you sing it in your head or say it in your head is up to you. But I know, I clearly remember like sitting at the AP exam and just thinking to myself, low, D high, less, high, D low, then draw the line and down below, the bottom squared will go. Just because it is easy to mix things up in the quotient rule, especially that numerator. So I'm going to find the derivative of this one. So I have x to the 7th over sine of x. So with my quotient rule, I have low, D high, less, high, D low, da 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 da, then draw the line, and down below, the bottom squared will go. Any questions on the quotient rule besides asking me to sing that for you again? Cool. Well, when we are back in person, I will probably make you sing that song with me with a mask on, because it's kind of a rite of passage.
Like saying like the low D high and stuff, like what is that? I don't understand. Like,
so when I'm looking at my fraction, I have like, this is the low part, this is the high part. So when I'm talking about, I know it's hard to see my finger point when you're just looking at the screen, but I have low D high, derivative of the high, less high D low, derivative of the bottom. Draw your line, and down below the bottom, so the original denominator squared, will go.
oh, so it's like saying like when you say D, it's like the derivative.
Yeah,
of
derivative of.
Okay.
There's just too many syllables to fit derivative of in a song.
Yeah.
So yeah, so there's a song. And then I'll bring you this. So I know it looks kind of weird because we just learned the quotient rule, and then I say, hey, but if you can avoid the quotient rule, that's what you want to do. But that is what you want to do. So the quotient rule you saw is kind of like an awkward formula. It's especially awkward when we start doing applications of these. So realize finding the derivative, like I know that's what we're focusing on this unit, but that's usually just the first step of a much, much, much longer problem. So sometimes you can't get around it. Sometimes you are forced to use the quotient rule. But my suggestion to you is if you can avoid the quotient rule by using algebra to rewrite the problem, it will make your life a whole lot easier as our problems get more and more complicated. What I mean by that, in this first example, I have y is equal to 5x over 6. Like we looked at one like this yesterday. You could technically do the quotient rule. So you could say, all right, low D high, less high D low, draw the line, and down below the bottom squared will go. Not too difficult to simplify, but that is how you will find the derivative if you're using the quotient rule. The easier way to do that problem is say, hey, 5x over 6 is just 5/6 of x. That's the same function. I know the derivative of this is just going to be 5/6, and I don't have to worry about really simplifying anything. Same thing for the second one. Like you could do the quotient rule. It's not a very pretty problem, but we have like low D high, less high D low. Draw the line, and down below the bottom squared will go. And then you simplify that. But being a calculus student, you know that there's going to be an easier way to do that problem. So you could say, oh, well, this is just the same thing as saying 2/3 of x to the -4th power. And I know that derivative is -4 comes down in front. So I'll have a -8/3 and then subtract 1 from the exponent. That way is going to be a whole lot easier when we start doing our applications and having to worry about simplifying the quotient rule. The last example I want to show you of kind of simplifying but instead of using the quotient rule is this third one. So again, you could use the quotient rule. If you use the quotient rule, again, it's kind of a lot of simplifying. So I have low D high less high D low. Draw the line, and down below the bottom squared will go. And so if you did the quotient rule, like be my guest, but you're going to have to FOIL twice, distribute a negative, combine like terms, factor, cancel to get to a simplified answer. Also, if we get to the point where we start actually using the derivative to solve problems, like you will have to play with that derivative. Where it's a whole lot easier, this is a monomial, so I know I can just divide through. I can basically think what this would look like if I split it up. And we can split it up just because it has a single monomial in the denominator. And then simplify first and then find the derivative. So 10 divided by 5 is 2. X cubed over x squared is x plus 4/5 x over x squared is x to the negative first. So my first derivative would simply be 2 minus 4/5 of x to the negative 2. This derivative is a whole lot more friendly to use than that beast we wrote down, or I wrote down in red. Those two answers are equivalent. I'm not going to waste time simplifying that red answer, but those two answers are equivalent. So again, sometimes you can't get around using the quotient rule. You will be stuck using it. Other times, if you can simplify it, that is what you want to do first. Any questions so far?
I'm confused how you got from 2x plus 4/5 x to the negative first to the derivative.
From this step to the last step?
Yeah.
I just used the power rule. The derivative of 2x is 2. And then 4/5 x to the negative first, I used the power rule, so that negative 1 came down in front. And then I subtracted 1 by the original exponent.
Okay, thank you.
You're welcome. So that is the product and the quotient rule. Those rules do give rise to some other problems that we know. So back to trig. Yesterday we learned about sine and cosine. Today we're going to start with learning tangent and cotangent. And I want to make the proposal that we actually can find the derivative of tangent and cotangent. Any ideas of how we can use rules we already know to find the derivative of tangent or cotangent?
Use the quotient rule. With like
We can use the quotient rule. How do I know I can use the quotient rule? What is tangent? What's another way of writing tangent?
sine of x over cosine of x.
Sine of x over cosine of x. Same thing for cotangent. We know it's the same thing as saying cotangent. Not that, it's the same thing as saying cosine over sine. And we do know the derivative rules for sine and cosine. We also now know the quotient rule. So we can use that to start finding the derivative of tangent. So I'm going to do the derivative of tangent first, and then I'll let you try cotangent on your own. So I have low d high, the derivative of sine is cosine, less high d low, the derivative of cosine is negative sine. Draw my line, and down below, the bottom squared will go. So I can start simplifying this. Well, I have cosine times cosine, which is of course cosine squared. I have minus sine of x times a negative sine of x. Some of you are seeing where we're headed with this. And I have sine squared of x. And all of this is over cosine squared of x. Please don't do bad algebra. You cannot cancel out those cosine squareds because you have a plus sign in the numerator, so you can't cancel across plus or minus. But what can you do in that numerator?
It's 1.
It's 1. So the derivative of tangent is just 1 over cosine squared. Or all of you made it out of pre-calculus. What do we know is another way we can write 1 over cosine squared? What is
Squared of x.
secant squared of x? Correct. So that actually adds another rule for us. Normally when we take the derivative of tangent, we don't want to have to do the quotient rule every time. So this becomes a rule that you can just memorize. The derivative of tangent is secant squared. I know personally, like if you're ever like on a test and your brain just freezes and you can't remember the derivative of tangent, you at least now can kind of figure it out pretty easily. But we can also find the derivative of cotangent the same way. So we have low d high less high d low. Draw my line, and down below, bottom squared will go. So this is going to give me negative sine squared of x minus cosine squared of x all over sine squared of x. Well, this one looks really, really close to what we did in tangent, but right now, as written, that denominator is not equal to 1. But what can you do so you can simplify that numerator? I said denominator and numerator.
Factor out a negative.
Factor out the -1. So when you factor out that -1, you can kind of see why that trig identities unit from pre-calc is a little bit important now. Well, sine squared plus cosine squared is just 1, so we're left over with -1 over the sine squared of x. Well, -1 over sine squared of x can just be written as what? Negative cosecant squared of x. And that's going to be another rule that we can memorize and use. So I'm going to go in, I'm going to skip a slide and jump to here. So we have 6 trig derivatives we'll use fairly commonly. Sine and cosine we talked about yesterday. The derivative of sine is cosine. The derivative of cosine is negative sine of x. And now we just found the derivatives for tangent and cotangent. Again, these are rules we want to memorize. The derivative of tangent is secant squared of x, and the derivative of cotangent is negative cosecant squared of x. I did mention yesterday, any of your derivatives of cotrig functions will always end up being negative. So then we do want to find ways to figure out rules for secant and cosecant. And so that's going to be your first kind of classwork activity. I want you to try it on your own. So go ahead and see if you can find the rule for secant and cosecant by using your derivatives of sine and cosine and the quotient rule. And again, I'm saying we can use the quotient rule because secant is of course 1 over cosine and cosecant is 1 over sine. So see if you can use the quotient rule to come up with a usable rule for secant and cosecant. Often. So secant is 1 over cosine. So I have low d high, make sure you remember that the derivative of a constant is 0. Less high d low, all over the bottom squared. So we end up that the derivative of secant is sine over cosine squared. We know from trig identities that there's lots of different ways that you can simplify that. The most common way we are going to write that is that sine over one of the cosines makes tangent. And then that other cosine left over in the denominator, 1 over cosine, is going to make secant. So we're actually going to memorize as a rule that the derivative of secant is tangent times secant. And then same thing with cosecant. We go and do the derivative using the quotient rule. We simplify it. We see a negative shows up, which is what we should expect when we do the derivative of a co-trig function. And then we have a cosine over sine, which is cotangent, and then the other sine left over in the denominator is going to be cosecant. Now, you don't want to have to do the quotient rule every time you take the derivative of secant and cosecant, so those are rules you definitely want to have memorized. So to finish filling out our 6 trig derivatives, The derivative of secant is defined as the tangent of x times the secant of x, and that could be written as like secant of x, tangent of x. That order doesn't matter because you're multiplying. And then cosecant is negative cotangent of x, cosecant of x. And again, this is the derivative of a co-trig function, so it ends up being negative. Any questions on any of the rules we've looked at today?
On the extended product rule,
Uh-huh.
there was the x plus 2 as one of the factors, and I just want to make sure I was following along for how you did that. You took the derivative of x and then the derivative of 2.
Yes, so like
to
the
get just the
derivative
one.
of x would be 1, and then the derivative of 2 is a constant, so it went away.
I just wanted to make sure I was following along. with
Yeah,
what you
no,
did
you're
there.
good. Any other questions on any of the notes you took today? All right, so I'm not gonna set you free yet, checking the time. Okay, so your homework tonight, like I'll go ahead and say that, so I'm not rushing. I am gonna go ahead and assign homework 3, so you have homework 1, homework 2, and then you have this homework 3. You are doing multiples of 4, so it's actually not that many problems, like 4, 12, 16, that first set's only 3 problems. If you do need more practice with the product and quotient rules, you can actually start homework 7 now. You can't do all of it, but you can do about half of homework 7, and that's just if you want more practice with these basic rules. But for now, for the last part of class, just to kind of check in your understanding, go ahead and try to find those 3 derivatives for me. The first one I think is pretty straightforward. The second one, I do want to give you a hint on how to rewrite the denominator. And the hint I'll give you on how to rewrite the denominator is this is the same thing as saying the square root of 5 as a coefficient times x to the 1/2. And then the 3, I typed in the hint. For number 3, this is the cosecant squared. We can't use the power rule because this is a function squared, not x squared. So you would want to rewrite it as a product. So you want to rewrite it as cosecant times cosecant. So go ahead and start those problems for me. It is 1 o'clock, so I know class ends in 10 minutes. So after a few minutes, I will go ahead and start putting up the answers so that you have them before class ends. And then basically, not tomorrow, but on Monday, we'll regroup and also look at our first application we have for the derivative. And then your quiz is actually next week as well on Wednesday over some of these basic rules. But go ahead and try those 3 problems for me right now. Feel free to unmute your mic if you have any questions before I put the answers up. And don't worry about simplifying your answers, really. All right, guys, so I jumped the gun a little bit and started working those out. So that first one, that 5 secant, is just a constant multiple, so I just have the 5 came across. The derivative of secant is tangent of x times the secant of x. Sine times cosine, and use the product rule, so I had the first times the derivative of the second, and then plus the second times the derivative of the first. Again, those order doesn't really matter. 2, I think, is the one that's like the ugliest derivative. So again, the square root of 5x, you can think of as the square root of 5 times the square root of x. And we know x is just the square root of x is just x to the 1/2 power. So I have low d high less high d low. The 1/2 came down in front. And that's wrong. Let me fix that. The 1/2 came down in front, and that square root of 5 was already there. So there we go. The square root of 5 over 2x to the negative 1/2, all over the bottom part squared. The square root of 5 squared is just 5x. You could rewrite that one. It wouldn't get much simpler, but just make sure you don't cancel across that minus sign. So I would just leave it like that, kind of ugly. And then 3, we can think of that as cosecant times cosecant. So I have the first times the derivative of the second plus the second times the derivative of the first. Cosecant times cosecant is cosecant squared, and it's negative, and those two terms are identical, so I could combine those and write it as a negative 2 cosecant squared of x cotangent. Any questions on those problems?
For the first one, could you have simplified the sine squared of x and the cosine squared of x to 1?
No, because that's a negative sine squared.
Okay.
You could use a double angle identity to simplify it, but I doubt anyone will want to go that far. But remember, it's just positive sine squared plus positive cosine squared, which is 1.
How did you combine the stuff for number 3?
3, so the first step is I multiply, like this is all just multiplying, so I can multiply them together and it becomes negative cosecant squared of x cotangent. Like we're not distributing because there's no plus sign in between that parentheses. And both of those end up being the same. So it's like I have negative 1 over here and then a negative 1 of the other. So I can combine them together to become negative 2 of all the trig. Any other questions?